Hello and welcome back to the channel. Today we're going to be looking at strange quarks from AQA A-level physics. We're going to be looking at what they are, what the quantum property they called strangeness is, and we're going to be looking at the history of quarks themselves to dive deeper into this. Finally, we're going to be looking at what strange matter is. Strange matter is purely hypothetical, theorized to occur, be produced in the cause of quark gluon, this quark gluon plasma in very extreme stars or around after. These are stars which are typically much more extreme than even neutron stars. But even then, strange matter this is purely hypothetical. There's no evidence for strange matter existing in the universe, but it is a fun concept to think about because it has also been theorized that strange matter could possibly be more stable than our regular matter, which means that if strange matter was to come into contact with regular matter, it would then sort of change that matter into strange matter as well, because it would be so stable. But again, that's purely hypothetical. So first, we'll go over a quick A-level recap. So we see that our strange quark has this mass. It is heavier than both an up quark and a down quark. It has a charge of our strange quarks have charge -1/3. They have the quantum number strangeness, which is -1 for our strange quark, the opposite for our anti-strange quarks. So now we're going to look at what this quantum property strangeness is and why even these quarks were called strange to begin with. So first we're going to go back to the 1940s, 1950s. Here, after World War II, scientists began discovering a whole range of new particles in what was called the particle zoo. Now, scientists theorized that all these new particles they're discovering weren't going to be all fundamental particles. They wanted to find something in common with them, so they wanted to group them together to try and see if there were any underlying fundamental particles between any of the groups. And one of these newly discovered particles were the kaon and the lambda hyperon. These were produced in the atmosphere when cosmic rays interacted with with protons. So here, from this diagram, we can see our pion here, proton here, and we can see that they're interacting through the fundamental strong force, which we're also going to look into in a bit. And then when these strange particles were produced, scientists immediately noticed that these particles had quite long lifespans compared to when they're produced. So one thing we know about the strong force is that it occurs over very, very short time spans. The strong force is 10 to the minus 23 seconds, whereas the weak force occurs over a much longer time span of 10 to the minus 10 seconds, which gave scientists a clue that the weak force was at play. These particles are being produced in very high energy collisions through the strong force, but only decayed through the weak force. Another clue that helped scientists was the fact that when the kaon, for example, decayed, it was decaying into pions, neutrinos, or muons. And we know that, for example, neutrinos, the only way that you could get a decay with a neutrino being produced is through the weak interaction, because neutrinos themselves have no color charge, which is needed for the strong force, and they also have no electric charge. They are neutral, which means that the electromagnetic force isn't at play. They don't have enough mass for gravitational force to be at play as well. So the only conclusion was that the weak force was at play. Now, from the diagram, you can see that that a weak decay took place, and the kaon and hyperon were produced. This is called associated production, where these new particles didn't show up one at a time, but rather in pairs. The two scientists working on this, Murray Gell-Mann and Abraham Pace, suggested a new quantum number called the strangeness charge existed and had to be conserved. Now, the one thing we should know about quantum numbers is that quantum numbers were introduced to summarize regularities in reaction symmetries rather than to describe underlying constituents. So what this means is that when scientists saw these strange particles being produced, the quantum number strangeness simply refers to the fact that there was something being conserved in these strange particles that forbade them from sort of decaying through the strong force, meaning they had to be decaying through the weak force where they could change quark flavor, which means that they could say go from a down quark to another quark, for example. But the weak force had to be at play. And that's sort of the reasoning behind why they were called strange quarks in the first place. Later on, when we look at the timeline, this is going to make more sense. But essentially, our strange quarks were called strange because of their long lifespans. Scientists initially didn't know what quarks were, so they're simply looking at the kaon and lambda hyperon at face value, and were just simply saying that these were strange particles because they didn't decay through the strong force, they could only decay via the weak force. And we know that we can see that the kaon and lambda hyperon, they have an anti-strange quark and a strange quark. So the anti-strange quark has strangeness +1, and strangeness and the lambda hyperon has strangeness -1, which means that strangeness overall has been conserved. There is no violation of quantum numbers, which is essential for the strong force interactions. Now, to be clear, what we've learned at AQA A-level physics is the residual strong force. Which is basically called the strong nuclear force. But we can see that the residual strong force and the fundamental strong force are slightly different. They are the same force, but it's just the fundamental strong force is sort of looking deeper into the residual strong force. So, the fundamental strong force has the exchange particle of the gluon, which is this here. This is a gluon. Gluons are the exchange particle for the fundamental strong force. For the residual strong force, the exchange particle is the pion. This affects nucleons. This is going to be our proton, and this is going to be our neutron. So that's these are the particles which the residual strong force affects, and the fundamental strong force affects quarks. So as we can see here, this is what our neutron looks like, and this is called the gluon flux tube. So in order to keep the quarks from, say, flying out everywhere, what the fundamental strong force does is it keeps them together by constantly exchanging these gluons and keeping them really close together. And also, the fundamental strong force affects all particles with something called a color charge. Now, this dives slightly into quantum chromodynamics, so I'll give a brief overview of what that means. Essentially, what quantum chromodynamics tells us is that for, let's say, our baryons, they must maintain at all times something called color neutrality. And what this means is that we give so the quarks themselves don't have an actual color in of themselves, but we, as an analogy, say that, for example, this down quark would be red, this down quark here would be green, this up quark would be blue, and that the total sort of color that they combine to make is going to be a neutral color, not going to be blue or green. And also, as a fun fact, the gluon also carries this color charge, and so this is how our kaon and lambda hyperon are produced through the fundamental strong force. This is also the reason why we never see quarks in isolation. This is due to something called quark confinement. What happens is when we try and separate these two quarks, the strong force will counteract this until we supply enough energy into the system that a quark-anti-quark pair can be created to ensure that we don't have quarks in isolation. So this is again fundamental. So let's say we try to take this down quark out from the neutron, we would have to supply enough energy that, say, we could replace this down quark with something that would maintain the color neutrality of the neutron and also the meson, which would be produced when we take the down quark out. So there will be a replacement here and an anti-quark down quark that will pair with this one sort of there. Okay, and also, by the way, the colors here aren't going to be fixed, they're going to be constantly changing, but the color neutrality is what matters. The colors must remain constant. And again, we can see here that this is just to recap, this is what our kaons look like. This is a K plus, K neutral, and this is going to be a K minus. Our kaons always have either a strange or an anti-strange quark paired with a up quark or down quark, or anti-up or anti-down quark. And then now we're going to look at a timeline of these events to try and further understand this, and also we're going to look at what strange matter is and what strange stars could possibly be.